Okay, so this is the second half of chapter 1, and we're going to talk specifically about measurements in this part of the PowerPoint, the second half of the chapter. What is a measurement? It's the comparison of a physical quantity to be measured with a unit of measurement. So that's a lot of measures. But the idea is it's a fixed standard. You know, if I want to measure the length of the table, I'll use a ruler. A ruler has you can get a ruler in metric and English units. If you had a yardstick, it would be in inches and feet. A metric stick would be in meters and centimeters, etc. But anyway, the main thing is, so you're comparing it to something that's standardized. If I measure a length of a table and I said to you, well, that's 27, you wouldn't know what I was talking about. I mean, you might have an idea, but you wouldn't necessarily know. You know, I could mean 27 inches wide. I could mean 27 feet tall. I could mean 27 centimeters tall. I could mean 27 years old. I could mean a whole lot of things. So we need to know what the fixed standard is that we're comparing to. So just keep in mind that in science, a number without a unit of measure is useless. You always need to put your unit. There's maybe a 0.01% of the time there is no unit involved, but almost 99.99% of the time there is a unit. Make sure and put it. I take off points if you don't put units. So speaking of units, these are our standard units that we'll be using in chemistry. In 1960, the General Conferences of Weights and Measures adopted this international system of units. So a lot of countries use it all the time. Of course, in the United States, we use it in science, but not in our regular everyday life. So these are based on the SI units. Here's our standard one. So length is always measured in meters with the symbol M. Mass, interestingly, uses the kilogram rather than the gram, but this is the standard SI unit, kilogram. Well, often in class we'll be using grams because it's a more useful unit. Time is in seconds. Temperature is in Kelvin, which we'll talk about later at the end of this chapter. Kelvin is a temperature. We have Fahrenheit, Celsius. Kelvin is actually a third type of temperature. Notice that the symbol doesn't have a little degree symbol. So Celsius and Fahrenheit, you put the degree symbol, but Kelvin we don't. Amount of substance, the unit is the mole. That's a lot of what we'll talk about the rest of this semester. These last two we don't really use in chemistry. Electric current is the ampere, and the luminous intensity is the candela. We won't be using those. But you might be saying, what about volume? Well, volume is a derived unit, so we'll look at that in a minute. Okay, so the SI units use the metric system, and we know the advantage of the metric system is that it's decimal, so everything's based on 10. I'm sure you're already familiar with the fact that inches, feet, yards. I couldn't tell you how many inches were in a mile or how many feet were in a mile or whatever. There's no standard transition, and so the metric system is superior for that reason. We can use these prefixes to indicate a particular amount, and so these are all the powers of 10. Now there's more of them. We can go smaller than pico, we can go larger than mega, there's tera, there's giga, but these are probably the most common ones that we'll use in chemistry, and some not as much as others. But so mega, let me get my pen working here. So mega is a million. So that's a very large number. So if I have a megagram, I have 1,000,000 grams. Kilo, of course, is 1,000, 10 to the third, or 1,000. If I have 1,000 grams, I have a kilogram. If I have a kilometer, there's 1,000 meters, so forth. Deci, there's a few here in between, but deci is one that we use, probably not so much, but deci is 10.1 or 1/10. So 1/10 is a decimeter. 1/10 of a meter is a decimeter. A centi then is 0.01 or 1 over 100. Centimeter, there's 1 centimeter is 1/100th of a meter. Millimeter is 1 over 1,000. Micro then is 1 over a million. 1 over 1 million. Or 0.000001, so that's very tiny. Note that this is actually a Greek symbol mu, so you can sort of write it like that. Sometimes you may have seen in other situations micro is sometimes abbreviated MC, but we're going to use the mu in chemistry. Nano then is 10 to the minus 9th or 1 over 1 billion. And then a pico is 1 over 1 trillion. So that is, you can imagine, that's really, 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 really tiny. We don't use that very much. But nano can be used because, for example, wavelength is in nanometers. 1/1 billionth of a meter. The way that you can use these conversions, and we'll be talking about conversions later, but you can say one of these equals this many of the standard. So if I said I have 1 megagram, that means there's 1,000,000 grams. If I have 1 kilogram, I have 1,000 grams. If I have 1 decigram or decimeter, I have 0.1 meters. And so this is a conversion. One of these will equal this many of the standard unit. So that can be helpful to remember that. We can put together the prefix and the unit, which is, I've kind of already been doing that. So, if I have 10 to the minus 9th grams, then that's a nanogram. 1 nanogram equals 10 to the minus 9th grams. If I have 10 to the 3rd meters, it's the same as a kilometer or kilometer. So 10 to the 3rd meters is a kilometer. 10 to the negative 3 liters is a milliliter, milli. If I wanted to express 6.0 times 10 to the minus 2 using a prefix, so in this case it's already written out, 10 to the minus 2 we know is centi, and so this would be 6 centimeters. If I want to express 3.76 milligrams, since milli is 10 to the minus 3, let me see if I can't find my pen here. Okay, 10 to the minus 3. Then this would be 3.76 times 10 to the minus 3 grams. So 3.76 milligrams is the same as 3.76 times 10 to the minus 3. So you can convert back and forth. Now, yes, technically I could also write this as this. These are the same number, but this is sort of easier because if you remember the prefix and you remember the exponent, then you can do it really carefully. Same thing here. This is 0.060 meters, which is the same as 6 centimeters. Okay. All right, like I said, we talk a little bit about temperature. The Fahrenheit scale, again, is what we use in the U.S. Every day. Celsius scale is what we use in science and chemistry. If you want to convert back and forth, now usually we won't have to convert back and forth, but if you want to, this is the formula that you use. If you have if you want to know what Celsius is and you know what Fahrenheit is, you use this formula. First you have to subtract 32 and then divide by 1.8. Or if you want to know the Fahrenheit, you take the Celsius and you multiply by 1.8 and then add 32. So let's say right now in my office it's 75 degrees Fahrenheit. So if I want to figure out what is that in Celsius, I would take 75 minus 32, which gives me 43. So this would be 43 divided by 1.8. And that would be 24 degrees Celsius. I can't find my pen sometimes. Okay. Again, let's say that you can see where it's based on. You can see that, like, if you had 0 degrees Celsius, 0 times 1.8 is 0, which is the same as 32 degrees Fahrenheit. So it's the difference is this 32. But let's say, you know, I was looking at somewhere in Europe and it said, well, today it is 42 degrees Celsius, and I wanted to know what did that mean in Fahrenheit. Well, first thing I would do is multiply 42 by 1.8, and I get 75.6. I can't find my pen again. 75.6, and I add 32, and I get 107 degrees Fahrenheit. So maybe I don't want to go there today. We'll talk about rounding, and I kind of rounded 7. So this is about 76 plus 32. So actually it's closer to 108 degrees Fahrenheit. I don't think I want to go there today. Sometimes I've seen temperatures like that in Palm Springs where my uncle lives, and I think I'll go in the winter when it's not quite so hot. Anyway, this is how you would convert. Like I said, mostly we'll be measuring everything in Celsius and mostly using Celsius, so it won't be very often that we'll be using these conversions. But one that we will use is the Kelvin temperature. So like I said, Celsius is the one that we usually, sometimes you'll hear it called the centigrade scale, but Celsius is most likely. It's the temperature scale that's most often used. But probably the SI base unit is actually Kelvin. The Kelvin is called an absolute. This is important. It's an absolute scale. Absolute means basically 0 equals 0. Now, when we're talking temperature, and again, that's something we'll learn a little bit later, temperature has to do with molecular movement. So basically, so the faster molecules move, the higher the temperature. Well, then on an absolute scale, 0 degrees Kelvin means that all molecular motion has stopped. So 0 is 0. You know, 0 degrees Celsius, there's still molecules moving around. And so sometimes we need this absolute temperature scale because, you know, we want to know when I get to 0, I'm done. So like weight is an absolute scale, because if you don't put anything on a scale, it doesn't weigh anything. If you put something on there, it weighs something. So that's an absolute scale. Temperature, the Celsius scale is not absolute. So the Kelvin scale is. And the conversion from Celsius to Kelvin is just really simple. The Kelvin scale is actually the Celsius scale that's just offset by 273.15. So if you want to know what the Kelvin temperature is, you just add 273.15 degrees, and we get Kelvin. So, you know, if we saw earlier that my room was 24 degrees Celsius, and I add 273. Now, again, we're going to talk about significant figures and decimal places, but let's kind of leave that off. So that would be 7. So that would be 297 Kelvin. And again, notice I don't put the little degree symbol, just put the K. So this is important. You're going to have to be able to convert from Kelvin. And of course, if you already know the Kelvin scale, you subtract 273 to get the Celsius scale. The Fahrenheit scale obviously has a different degree unit, and there's like 9 Celsius units for every 5. I'm sorry, 9 Fahrenheit units for every 5 Celsius units. So that's why they don't match up where the 1.8 comes from. Okay, anyway, we have other units that we need to know about, derived units. So these are based on the units we already have. So for example, you all know that area is length times width. So, you know, if I have a square here and I want to find the area, I'm multiplying the length times the width. Well, the length will be measured. It's actually a length times length, so it's two lengths. So if this is measured in meters and this is measured in meters, meters times meters will give you the unit meters squared. So that's the standard unit for area, meters squared. We can also have things like centimeters squared. inches squared, inches squared, feet squared, things like that. So it's just a squared unit. Volume is probably our most used derived unit, and we know that it's based on the volume of something. And again, if we have, let's write this over here. So this is area. Well, if we have a volume, say we have a cube, we know that volume is length times width times height, or a length times a length times a, where's that one? Length times length times length, length times length times length. I can't talk. And so that's meters cubed. Is the standard unit for meters cubed. Sometimes we'll see centimeters cubed. Cubic inches. A cubic inch is the English unit. Sometimes, just a little interesting side note, centimeters cubed is sometimes abbreviated like this, centimeters cubed, or a cc. You may also realize, you may or may not know, but a cc is the same as 1 milliliter. So technically, volume is defined in sometimes of length cubed, but then we convert it over to our unit that we're most used to, which is liters, milliliters. Of course, in the English system, they're gallons, cups, and everything, but we'll be using milliliters. So 1 cc or 1 cubic centimeter is the same as 1 milliliter. So chemists usually use liter. So like I said, a liter is the same as a decimeter cubed, and a milliliter is the same as a centimeter cubed. So if you can find the volume in terms of centimeter cubes and you need to know the volume in milliliters, just remember that they're equal to each other here. Density is another derived unit. So let's talk a little bit about density. You may have heard of it before. I'm sure you've heard, that things that are more dense will sink and things that are less dense will float. But what is density? Density is defined as the mass per unit volume. So in other words, density is the mass. You take the mass in terms of usually grams divided by the volume. The volume could be in different things. It could be in milliliters, it could be in liters, it could be in centimeters cubed. It'll depend on what we're measuring. But you take the mass in terms of grams and the volume, and maybe milliliters, something like that, grams per milliliter. And so density is a derived unit. So generally masses in grams. This is kind of standardization. It's not a hard and fast rule, but usually if we're talking about the density of liquid, we'll say grams per milliliter. If we're talking about solid, because a solid has a rigid shape, we often will use gram per centimeter cubed, but you can use those interchangeably because they're equal to each other. And then oftentimes gases density is in grams per liter, because it's so the density is so low that that there's tiny numbers if you use milliliter. So the liter unit can change, but basically it has to be, or the volume, but it's mass per volume. The density of water is 1 gram per milliliter. Actually, things are sort of defined. That's defined as 1 gram per milliliter at a particular temperature. It might change depending on the temperature, but we'll just kind of generalize and say water is 1 gram per milliliter. Lead is much more dense, so it's 11.3 grams per milliliter. It's one of the heaviest things. Air is, you can see, 1 gram per liter. Or if we convert to milliliters, it would be 0.001 gram per milliliter. So very, very much less dense than liquid. Gold is one of the most dense compounds. It's 19.32 grams per centimeter cubed. This could be in centimeters cubed too, up here, the lead, but density, as I said earlier in this presentation, or in the previous one, is a physical property. It's a characteristic of the substance without changing its identity. So water, has that density of 1 gram per milliliter. Density and weight are often confused. let me give you an example. If I said, someone might just say, oh, gold is weighs so much. Well, it really depends on how much you have. So density has to do with amounts. So if I asked you, for example, which is heavier, a pound of feathers or a pound of lead? Well, if you think about it, they're both a pound, and so they weigh the same. So that would be weight, a pound of feathers or a pound of lead. But if I asked you which would have a bigger volume, which would you have more of, a pound of feathers or a pound of lead? Well, you'd say you'd have a pound of feathers would be a whole lot of feathers, whereas a pound of lead would be a pretty small piece. And that's because lead is more dense than feathers. So you remember that you have to have both the volume and the mass. If I told you water wasn't so heavy, but if I had a pool, like people used to think, well, water's not that heavy, and they used to have water beds, put them upstairs. Well, if you have a whole lot of water, you have a whole lot of mass. So it depends on the amount. So again, here's water instead of feathers. A pound is a pound is a pound, but I've got a pound of lead will definitely have much less volume than a pound of water because it's more dense. So density has more to it than just weight. So here are some examples of density. Here's a straightforward one. If we have the mineral galena, which is lead sulfide, and we take a sample of it and we weigh it, and that sample weighs 12.4 grams, and then we measure the volume. This is something we'll do in lab. You can measure the volume in a couple of different ways, probably by putting it in water and by using volume displacement. But anyway, we know that the volume of this piece is 1.64 centimeters cubed. What's the density? Well, we know density is mass divided by volume. So we take the mass, 12.4 grams. We take the volume, 1.64 centimeters cubed, divide it out, round it, and we'll talk about rounding and significant figures in just a minute. 7.56, and the units are grams per centimeter cubed, which you have to put the units. In this case, it's just gram divided by centimeter cubed, so gram per centimeter cubed. We can also rearrange the equation. So let me draw this here. So we have density equals mass over volume. All right, so in this case, they're asking to calculate the volume. The volume, and this time you're given the mass, 65 grams of methanol, and we know the density. So for every 1 milliliter weighs 0.791 grams. So we want to know how many milliliters is 65 grams. So we can rearrange this equation and solve for volume. So the first thing I'm going to want to do is multiply both sides by volume to get that out of the denominator. And we'll have volume times density equals mass. So that's one other equation because that'll cancel. Now we know mass and we know density, and we're trying to find volume. So if I divide both sides by density, I will get that volume equals mass over density. The density will cancel. So what do we want to do? We want to take our mass, which is 65 grams. Our density is 0.791 grams per milliliter. I want you to notice what's happening with the units. I've got grams divided by grams, so they're actually going to cancel. And this is 1 divided by 1 over milliliter. So if you invert and multiply, you'll actually end up, milliliters will end up on the top. And we'll just do that, 65 divided by 0.791. And we get 82.2 milliliters. I think if I slide the show, there you go, 82.2 milliliters, 65 grams divided by 0.7. So again, this is, the grams will cancel, and I have 1 over milliliters. If I invert and multiply, I'll end up with milliliters. So that's density. You can rearrange this equation. So you can find volume, density, or mass if you know the other two. So let's talk about some words that often get confused. Precision. Precision technically refers to the closeness of a set of values obtained from identical measurements of a quantity. So what that means, if I weigh something, if I weigh it 3 times, how close are those 3 measurements to each other? Another way that you can think of precision is how many decimal places are you measuring it to. So if I had a scale that I could measure only to the ones place, that would be much less precise than if I had a scale that I could weigh to the 3 decimal places. And so sometimes precision can mean one or the other. I mean, if you're not, it's like the likelihood if I took something and weighed it on a more precise instrument would mean that my values should be much closer to each other if I measured it a number of times. So that's it. Kind of the precision can mean kind of both of those. So how close are the measurements to each other? And then accuracy is a related term, but it refers to how close is a single measurement to its true value. So you can definitely be precise without being accurate, and you can be accurate without being precise. So let's look at a couple of examples here. Let's say I weighed something and the actual value of that thing was 10.923 grams. So let's say one set of students measured this object 3 times. And each time, here's the measurements, 10.536, 10.537, 10.535. Now, you might not know what the actual value is, so someone might be saying, hey, this is great. Look at how precise we are, which you could get confused with and think, well, look how accurate I am. But you're not accurate because, in fact, very precise, because you can see the average of these 4 numbers is very close to each of them are very close to each other. However, it's not accurate because the actual value is 10.923. Now this situation might happen if the scale is not zeroed properly, so you're off by the same amount every time. So this is precise but not accurate. What if another group of students measured the same 4 things, the same thing 4 times, and here they measured, look at how off these numbers are. This is not a precise set of data. They're kind of all over the place. However, look at that value. The average of all 4 of them is exactly the true value. So that's just kind of lucky in my opinion. But anyway, this set of data is accurate but not precise. Of course, what do we want? We want precise and accurate. So we want them both. So we use something called significant figures to indicate the precision of a measured number or the result of a calculation if we're doing calculations. And so significant figures are really important in chemistry because we want to represent how good of a measurement your measurement is or your calculation is. How true to the actual value is it? Because I'll show you an example. Okay, so significant figures are defined as the digits in a measured number, or the result of a calculation, that include all certain digits plus one final digit that has some uncertainty. Okay, so let's talk about these significant figures. So let's say we're trying to measure this steel rod here. And you can see, if I put my pen here, my certain digits, I can certainly say that this rod weighs 9.1. But it's a little bit more than that. So it's definitely something greater than 9.1, but it's definitely less than 9.2. And these are my certain numbers because those are my actual markings. But you can see that the rod is just slightly to the right of the 9.1. So a significant figure then would be the extra digit. So if I were reading this, I'd say, okay, the length is 9.12. I would estimate that that's about 2/10 of the way between the 0.1 and 0.2. Now someone else might come over here and say, no, I think it's 9.13. Well, that's sort of the uncertain number, and that's fine, but you want to report it to one uncertain number. So again, I might say it's 9.12, someone else might say 9.13, but we know certainly it's between 9.1 and 9.2. And Now, probably you wouldn't say 9.18 because it's not that close to the 9.12. But anyway, that last digit, we're clearly able to read the two certain parts, 9.1. We estimate the last digit, which is the uncertain one. And those are the kind of measurements that you're going to be needing to do in lab. We always want to estimate our last digit and report it. Even if that last thing, let's say this was exactly on the line, I still want to get that last uncertain digit. And even if it was a 0, if it was 9.10, you would be estimating that last one. So all three of these digits, 9.12, are considered significant in this measurement. We'll talk more about this when we're doing labs. We'll be talking about how to read length, how to read volume, etc. So, but now I think that's pretty straightforward if you can measure something, but how do we keep the correct number of significant figures if we are doing some calculations? So let me give you an example of that. Let's say we found a piece of gold and we measured the weight, the mass, 23.76 grams, and we found the volume, 1.23 milliliters. And so we want to calculate the density, and we already looked at density, so we know that we can do that. To find the density, it's mass divided by volume. So I take my 23.76 grams and I divide by 1.23 milliliters. I put it in my calculator, and what do I get? 19.317077317, and it actually might go on, but my calculator cuts it off at that point. So this is too many significant figures because, you know, if you think about what we were just saying, we can't know the density that carefully to all those decimal places. These last ones are meaningless. So what we would have to do is round it. So, and we're going to talk about this in more detail, but in this case, I'm going to round it after the 3. Remember how to round. Find where you're trying to round to. You know, I want to round to the first decimal place in this case. Look at the next number, and I see so many people making that mistake. Make sure and look at the next number. If it's less than 5, you cut it off, so 19.3. If this number happens to be greater than 5, you round this number up. Anyway, in this case, we cut it off. So as you can see, if I wrote this answer, it wouldn't be very useful. I mean, it might be true that 23.76 divided by 1.23 is this number, but it's not going to give us a very good answer in terms of the density because we didn't measure the volume and we didn't measure the mass to that extent. So we can only do our density to the same significance. So let's talk about those rules. First of all, we have to determine what is significant when we are using numbers, if we hadn't measured it ourselves, if it's something that we're given. First of all, note that all non-zero digits are considered significant. So if you've been given a number and you want to know how significant is it, any non-zero digits are significant. So it turns out the zeros are the problem. Because zeros can be placeholders, or you can imply that, yes, I really did measure it, and I say that digit is a 0. So you really have to understand how zeros work. So if a 0 falls between 2 significant digits, then those zeros are also significant. So in this case, 1.005 has 4 significant figures. 1.03 has 3 significant figures. These zeros are significant. They're not just placeholders. If I have zeros preceding any non-zero digit, those are never significant. So in this case, these zeros are just placeholders. So I only have 2, 6. This has 2 significant figures. This number right here has 3 significant figures. So zeros between are significant, zeros before are never significant. So it's the zeros at the end that really give us the most trouble. If the 0 comes after a decimal point, we count them as significant because somebody's going to the trouble of saying, yes, I measured it, 0.0, 23.0, I measured it to that 1 decimal place. So you know it's significant. But the problem is if there's no decimal point, it's considered ambiguous. So for example, here, 0.0200, the fact that I can't get my pin on there. There we go. Okay, I can't find where it is. So the point, there it is. Okay, the 0.0200 has 3 significant figures. The 0 beforehand is not, but these 2 zeros, because they come after a decimal, are considered significant. I mean, otherwise, why would you bother writing them at the end if they're not significant? 3.0, yes, that's considered significant again, because that's 2 significant figures, because I'm telling you that number is 3.0. I measured it to the 10th place. If I just gave you this number, 10,300, it's ambiguous. It could, these zeros might not, we know that one's significant, right? Because it's between. But it could be that this person measured it and said, well, yeah, it's maybe around 10,300. Or they might have measured it really carefully and said, oh, yeah, it's 10,300 exactly, plus or minus 1. This would be the plus or minus 10th place, the ones place, the hundredths place. So it's kind of like, the plus or minus, where was it measured? And since this number, unless the person is right there where you can ask them, you don't know. A lot of times to get around that ambiguity, we put numbers into scientific notation because then you're forcing the decimal place and then you can determine it. So like if I wrote, instead of 10,300, I wrote 1.03 times 10 to the 4th, then I know, yeah, it's only 3 significant digits. Those last 2 zeros were just placeholders. But if I went ahead and wrote this number, 1.030 times 10 to the 4th, I'm telling you, I measured it that precisely to that 3rd decimal place. And so let's count that as a significant digit. So again, if you're not sure how else to show correct significant figures, the easiest way is to stick it in scientific notation, and then you know what it is because you got the decimal place, because we know any zeros after a decimal are considered significant. Okay, so that's how you figure out how many significant figures you have in a number. So now what are doing calculations with them? So we know that you can imagine that the least certain measurement limits your significance in the calculated amount. So, if you were really, really careful and you were trying to measure the area of or let's say the volume of a box, and you were really, really carefully on the first measurement, and you measured it to like 2 decimal places on the ruler, but your second measurement you just really estimated. You let your dog do it or something and didn't measure it very carefully at all. Well, the volume that you get by calculating isn't going to be any better than that least precise measurement. So that's kind of how significant figure rules come about. So the final answer should be reported to one significant digit or one uncertain digit, and you want it to represent the values that you had already. So if you're multiplying or dividing, what you do is you report the answer with the same number of significant figures as the measurement with the fewest significant figures. If we add or subtract, it's not as easy because you have to line up decimal places. So your result should not have more decimal places than the measure with the fewest decimal places. So let's look at that. So, and the one we did a little while ago, that if you go back and look at that slide, the mass had 4 had 4 significant figures, and the volume had 3, and so our answer had to have 3. In this case, our numerator, 14.0 grams, has 3 significant figures. Our bottom number, 102.4, has 4 significant figures. So our final answer should not have any more than 3 significant figures. So if you do the math, here's what you get on your calculator. But you want to cut it off at 3 significant figures. So this is your last decimal place here, so 3 significant figures. Remember to look at the next one. Because that's larger than 7, we're going to round up, and so it'll be 0.137 will be my answer. Don't forget your units, it's grams per milliliter, and so that's got 3 significant figures because we only have 3 here. If we only had 2 here, we would round it to two significant figures, or 0.14. So the value should represent the significance of the numbers used in your calculation. So again, multiplication and division is easy because you just use the same number as the smallest. Addition is a little harder because let's say we're trying to add these 3 numbers together. Well, since adding has to do with the ones place or the tenths place or whatever, the second measurement we measured to 3 decimal places. The first one we only measured to 1 decimal place, much less precise. The third one we only measured to the ones place. So our answer cannot be any better than our least significant, which is the 83. So we can only give our answer here to the ones place. So even though that's the true answer, 104.722, we would round that to 105 because we can't. There's no decimal places here. Now, if that were a decimal 0, then we could do it to the tenths place. But since there's no decimal place and no digits at all, we have to cut it off at the ones place. So these are just some things to keep in mind. There is a review sheet online for practicing significant figures and an answer key, so I would definitely recommend practicing some of those. We'll be looking at them in lab and show up from time to time. Now, if you have an exact number actually has no significant figures, or you could look at it the other way, it actually has infinite number of significant figures. So that's if you count something. So if I have 9 coins in a bottle, I mean I have 9 coins in a bottle. I don't have to worry about estimating it or rounding it or anything because it's 9. If I say there's 12 inches in a foot, that is that's actually, again, infinitely significant. That's a definition. There are 12.00000 inches in a foot, and so you don't have to worry. So if I was doing a calculation and I was converting from inches to feet, I would keep the same number of significant figures as my original value. I wouldn't worry about the fact that 12 only has 2 sig figs or that 1 foot only has 1 sig fig. Those don't get counted in our significant figures because they're infinite. So these exact numbers have no effect on calculation. You can ignore them. All right, the last thing we're going to look at is dimensional analysis. This is a really useful way of converting things, and this will be something that you will use. This technique is something that you should use throughout the whole semester, so it's a really good thing to learn from the beginning. It's really helpful because, like I said, every number in chemistry should have a unit. And so we can convert units very easily or do calculations where units are important by keeping up with our unit. So it's a good practice to associate units with each quantity. And you'll see that then you can oftentimes, if you're not sure what calculation you need to do, you can often match up your units to figure out if you need to multiply or divide, and then you can do the problem much easier. So the units will come out of the calculation. It'll be apparent where your error is if you are careful with this. A lot of people are very sloppy and won't do this, but if you take the care and really do this, it will be very. In fact, the homework system walks you through a lot of this dimensional analysis in chapter 1. You can work through this. So, all right. So dimensional analysis is also sometimes called the factor label method. You can use both names, either one. But it's a method of calculation where we use our units to convert. So I'll give you an example. If you want to convert 20 yards to feet, now I think you could do this in your head, but let's walk through the process so that you can see how to do it. You might just say, oh, well, there's, see, 20 yards, that means there's 60 feet because I know there's 3 yards in a foot. Well, yeah, but let's do it from, put it down. So here I'm starting with what I'm given. I say, okay, I've got 20 yards and I want to convert that to feet. So what do I know? I know this conversion factor. I know that 1 yard equals 3 feet. And again, significant figure wise, these are not important. But I do know that there's 3 feet per 1 yard. So if I multiply by this factor, and in this case I put yards on the denominator because that will actually, if I have a unit on the numerator and one on the denominator, they'll cancel out, just like a fraction would, like a 2 and a 2 would cancel out. They can cancel out. And then I've got feet on the top. That's the unit I'm trying to get to. And so if I multiply 20 by 3, I get 60 feet. And yes, that was probably something you could do in your head, but again, it's the process that I want you to see because in some calculations, it's not going to be that obvious and you want to be able to follow along. So if I multiply by 20 multiplied by 3 divided by 1, I get 60 feet, and these units cancel, and so the final units are my feet. Yep, so my yards cancel. So that ratio, 3 feet to 1 yard, is called a conversion factor. It's a definition. We know that 3 feet equal 1 yard. What we did is technically we took that 20 yards and we multiplied by a form of 1. So it didn't look like the number 1, but it was a form of 1 because we know that 3 feet equal 1 yard. And so the numerator and denominator were equivalent to each other. So it's like multiplying by a form of 1. So our answer is equivalent to our original value, even though it looks different. It just has new units. So units are really important and we have to be able to convert them. So again, because the numerator is equivalent to the denominator, it's like multiplying by a form of 1, and so the intrinsic value doesn't change. We can do this between, as you saw in that example, that was between 2 English units, feet and yards. This is a really helpful way to convert between US units and metric units. I'll show you on the next slide some of those conversions. And we can also convert between metric units and metric units. And as you'll see, we'll be using this even in other chapters where we'll be converting from one compound to another compound and using the same. So here are some relationships, US and metric units. Your homework, you may need to look, they may not give them to you necessarily on the homework. If it was on a test, since these are between US and metric, I would probably give you these. Now I won't give you the metric one, metric to metric, because those you'll have to know. That was earlier when we saw the centimeter to meter and things like that. But some of these I don't know off the top of my head, and I would give them to you. Like 1 mile is 1.609 kilometers. But these are conversion factors that you can use. Sometimes I've also heard like 2.2 pounds per kilogram, so they can be reversed too. But anyway, these might be helpful. So let's look at unit conversion. What you want to do is take the units that you're starting with, figure out what units you're trying to get to, and then find a conversion factor that compares the two. So here's kind of the idea. Take your given unit, find a conversion factor that has the 2 units involved, and then put the unit that you're trying to get rid of on the bottom, the desired unit on top. They'll cancel out, and you get your desired unit. So let's look at an example. What is the length in kilometers of a 500-mile auto race? So we start with what we know, 500 miles. There is the conversion factor between kilometers and miles, 1.609 kilometers per mile. And so our miles will cancel our units. So we want kilometers on top and miles on the bottom. And then the kilometers are our answer. Notice that here I had 4 significant figures, and so I keep 4 significant figures. So here's a little bit, sometimes you need more than one conversion factor, and you can just string them along. So what is a woman's mass in grams if she weighs 115 pounds? So I was able to find the conversion factor from pounds to kilograms, but not to grams. So I can first convert from pounds to kilograms because I know there's 0.4563 kilograms per 1 pound. So my pounds cancel and I get 52.2 kilograms. But what I need is I want to convert this to grams. So now I need to use a second conversion factor. And I know that there's 1,000 grams in a kilogram. So kilograms goes on the bottom, grams goes on top. Kilograms cancel. My answer will be in grams. Notice in terms of significant figures, we don't know if those zeros are significant or not, but since we started with 3 significant figures, we should only end with 3. So these zeros are not significant. This is probably an okay answer, but to be absolutely sure that you only have 3 sigs, you can convert it to scientific notation. So you can see 5.22 times 10 to the 4th. Now you don't have to stop after every conversion. In fact, you can actually do them all in one trial, as you can see here. So 115 pounds, first convert to kilograms. I know I'm not stopping there, so now I'm going to convert from grams to kilograms to grams. So I just multiply everything on the top, divide by everything on the bottom, and I get my answer. So you can string them along. What I would recommend, sometimes people will do one conversion factor and get an answer. Just keep that number in your calculator. Don't round after each step or you'll end up with rounding errors. So again, everything cancels and your units are grams. Density can be used as a conversion factor because it relates mass to volume. So for example, in this case, since, let me get this going. Since I know the density is 0.87 grams per mil, what does that mean? That means that if I have 0.87 grams, there will be 1 milliliter, 1.0 milliliter. So that's a conversion factor. That tells me that converts from grams to milliliters or milliliters to grams because they're equivalent. So density can be a conversion factor all in itself. So what is the mass of 1 gallon of rubbing alcohol in terms of grams? So I can find grams if I know milliliters, because once I know this conversion factor. So somehow I have to convert gallons to milliliters. Once I know milliliters, then I can convert using my density to grams. So I'm going to have to use a couple conversion factors here. Now, one thing to note is that there's sometimes more than one right answer. Like someone might say, well, I know how many liters are in a gallon, and you might just know that conversion factor off the top of your head and be able to use it, or you might look it up. But someone else might say, well, no, I don't know that. I know how many liters are in a quart, but I don't, so there's different ways of doing it. There's more than one right answer. Of course, there's wrong answers, more than one wrong answer too, but there's more than one right answer. So this is the way I did it, using the conversions that I had on that other chart. Said, okay, if I have 1 gallon and I know there's 4 quarts to a gallon, because I know this conversion factor, 1 quart equals 0.95 liters. So I'm going to convert from gallons to quarts, and then I can convert from quarts to liters. Now, I know that in order to get grams, I have to have milliliters, so I can convert from liters to milliliters. And then finally, I know my conversion factor, 0.87 grams equals 1 milliliter. Now, in terms of significant figures, like a lot of these are infinite, so we don't have to worry about these are now here you're only given 2 significant figures. Actually, I would have put it one, the 2 significant figures because that's implied in there, 2 significant figures. This one, notice that this example only used the 2 significant figures because we started with 2 significant figures. You can actually find a conversion here that has more. If you look back on that chart a few slides ago, it probably has more decimal places. But this person just used 2 because I only needed 2. If you use more, you still only want to use the same significance of the your original question. So since that has 2 significant figures, I'm using 2 in the end. But notice, okay, so I convert from quarts to milliliters and then finally milliliters to grams. You can see everything cancels out and my unit is grams. Do want to point out that it's really important if you convert a unit that's raised to a power, you need to make sure and raise the conversion factor to that same power. So for example, let me draw this cube here. You know, if you're talking about a cubic centimeter, actually, let's read this question. You know, here's my cube. I know the volume in terms of meters cubed, so that means meters times meters times meters, meters cubed. I want, in order to convert it to liters, the only conversion I know between the volume and cubic volume and regular volume, I know this conversion, 1 centimeter cubed is 1 milliliter. There's other conversions too, so you could do it other ways, but this is the one that is probably the easiest to use. But here's the thing, it's centimeters cubed, so once I find centimeters cubed, I can find milliliters, and then I can convert to liters, but I need to somehow convert meters cubed to centimeters cubed. So notice, since I have three lengths in meters, I have to convert each of them to centimeters, so be really careful about that. One way I can do that is by using a conversion factor for each meter. So this top here, so 5.4 meters cubed. If I convert 1 meter to centimeter, the second meter to centimeters, and the third meter to centimeters, I get centimeters cubed. So I mean, the units are just like numbers. You just keep track of them. So all 3 meters cancel 1, 2, 3. Because it's cubed, meters times meters times meters. So that's centimeters cubed, centimeters times centimeters times centimeters. Or you can use one conversion but cube it. So notice that my meters cubed and my centimeters cubed. So the meters cubed will cancel and the centimeters cubed will be my answer. So just be careful with that. So I've converted my meters cubed to centimeters cubed, and I know that my 5.4 times 10 to the 6 centimeters cubed is the same as milliliters, so I can convert that to milliliters. And then I know that I have 1,000 milliliters in a liter, so I divide by 1,000 to get liters. And so this is how many liters are in this many 5.4 meters cubed. So just be careful about the cubic. All right, so here's what you should be able to do in this chapter. Describe the scientific method, explain the law of conservation of matter. Matter can neither be created nor destroyed. Be able to compare and contrast solid, liquids, and gases, and that's pretty straightforward. Be able to identify something as an element or a compound or a mixture. Know the difference between chemical and physical properties, chemical and physical changes. That's both of those. Difference between an extensive and intensive property. Know the difference between precision and accuracy. Be able to figure out the correct number of significant figures. Be able to use scientific notation to represent them if you need to, or be able to read scientific notation. That's not really in this chapter, but you kind of already have to know how to do that to be in this class. If you need help with that, let me know. Be able to apply rules of the significant figures to report the correct value in the end. Be able to convert temperature changes from one to another, and distinguish between mass and weight. We did that earlier. Use the density equation to solve for density, mass, or volume if you're given the other two, and then be able to use dimensional analysis to convert from one unit to another. That's the end of chapter 1. Thanks for listening.